We live in a dynamic world filled with different forms of motion. If we hope to understand this motion, we have to be able to analyze it with respect to a set reference axis. This is where kinematic analysis comes to play. Using kinematic equations, we can analyze a range of inertial and non-inertial problems. In this video, I aim to teach you how to apply this analysis method to a range of problems that you will encounter in any engineering mechanics course. I will not derive any equations for this topic, as I believe the method by which you apply the formulas is a much more fundamental and important concept. Hopefully, we all learn something. Okay guys, I hope you enjoyed that introduction. So, now we can get to the actual formal introduction of the content. So from 1300, you've probably realized that the displacement of A is equal to the displacement of B plus the relative displacement of A with respect to B. This is illustrated with this vector diagram, which shows the displacement of A in its components there, the displacement of B plus the relative displacement. That's pretty simple to understand, and that is a fundamental equation which is used to derive equations for velocity and acceleration. I'm not going to go through the proof because it's a bit lengthy for this video, but I will touch on the formulas. So for velocity, it can be expressed in a similar manner. So the velocity of A is equal to the velocity of B plus the relative velocity of A with respect to B. And what we do when we're analyzing problems is we treat the velocity of B component as a linear velocity and the relative velocity of A with respect to B as the angular velocity. So that's a turning motion about A. So a principal concept is that if you've got any object, the angular velocity and angular acceleration will be constant no matter what point you take on that object. So now, if we apply this, you know that the velocity of B is going to be the linear path, so there's your path there, if that's state 1 to state 2, and then the relative velocity of A with respect to B will be B rotating about A, which is what gives this body that final orientation, that turning moment there. So now, if we move on to the expanded form of the velocity equation, this will be your complete equation. So, remember these two concepts, these two values rather, stay constant in all these equations. It's only the relative velocity of A with respect to B that changes. So we still have the rotational velocity there, plus we've introduced a v-rel term, which is, say if you've got a collar on a rod and the collar is sliding across the rod, then you'll have a relative velocity between the collar and the rod, so you have to introduce this relative velocity term. So if you've got a rigid body, which means that the displacement between 2 points on the body are not changing, then you just eliminate the v-relative term and you end up with this equation, which is simply velocity of A is equal to the velocity of B plus omega AB, which is the angular velocity, crossed with the relative displacement of A with respect to B. So there you've got your angular component and there's your linear component, as I talked about before. Acceleration can be expressed in a similar way using this formula, and then you've got your linear acceleration plus the accelerations resulting due to the rotational motion of the body, which will be your centripetal acceleration, and you've got your angular acceleration. An a-rel term will also be introduced along with 2 omega v-rel. This is your Coriolis acceleration, which will be touched on further in the course. And this is your final equation used for accelerations. So notice for rigid bodies you eliminate the v-rel term because the v-relative and the a-relative are 0, so you just end up with that part there, which is shown there. And that's used in rigid body. Now just some notes on solving problems. The first thing you want to do is you want to set the sign convention. So you may use rectangular coordinates or you may use polar coordinates. Either way, you want to set it and you want to keep it constant throughout the question. So if you were to use x and y coordinates as shown here, then your z direction will be determined by pointing your fingers at the x axis and then calling them towards the y. So in this case, this positive z direction will be out of the page. And always, positive rotation will be dictated by the right hand rule. So if you point your thumb outside the page, positive rotation will be counterclockwise, which is shown there. So the next thing you want to do is you want to break up the given data into the assigned sign convention. This will make cross products a lot easier, which is used in the kinematic equations that I showed you earlier. The third thing you want to do is you want to apply the formulas that I showed you earlier to determine the different components of velocity and acceleration. So you may start off at like a pin joint or a given point, and then you work your way across the question to get the resultant answer. So I mentioned here that you want to use constrained motion information. So a pin joint, for example, the velocity and acceleration at that joint will both equal 0. That's simply because it can't go anywhere due to the pin. Another example of constrained motion would be, say, a piston moving up and down in a cylinder, and you've got a connecting rod there. You know that the velocity and the acceleration of the piston can only be in the y direction, as shown there. So you would use that direction, and then you can split the equation up into the I and j components to figure out your answers. Okay, so I'm just going to go through a quick problem with you guys. So in this example, we've got a wheel which we're given the velocity of the center to be 5 meters per second to the right. And with all wheel problems, the point at which the wheel contacts the ground has a 0 velocity, as it's the instantaneous center of rotation. So what we're going to do is we're going to try and find the maximum velocity on the wheel. We're going to do this using the kinematic equations that I listed before. So here's just a diagram of the wheel. So we're given that the velocity at g is 5 meters per second to the right, and we know, based on our rolling problems, that the velocity at 0 is equal to 0 meters per second. So we use the velocity of g is equal to the velocity of o plus the relative velocity of g with respect to o. So that is instantly 0. So our equation simply becomes omega crossed with r of g with respect to o. So take note that r of g with respect to o, the relative properties are the same as the velocity properties, of the same order, I'm trying to say. So then we solve this for omega, and we get 5 on 0.5, because we're given the radius is 0.5. So we know that this object is rotating at 10 radians per second. Now remember that that is constant for no matter what point I take the rotation about. Omega is always constant for the same body. So now we're going to, because everyone knows that the maximum velocity point is at the top, because that's spinning about 0 the fastest, it's the furthest from 0. So velocity of a is equal to the velocity of 0 at o rather, plus the relative velocity of a with respect to o. So that's 0. So then that simply expands to omega crossed with r of a with respect to o. So if we take an I component as that direction and j as that direction, then we'll get a positive k as the anti-clockwise rotation. So hence omega is negative k because it's clockwise. So it's negative 10k, which is just omega, crossed with 1j. And then when we do our cross product rules, we'll get that is equal to 10I meters per second. So I know the maximum velocity is 10 meters per second to the right, at the top of the wheel.